From greetings from Seattle, Washington. I'm going to be talking about radiation interdiction at borders and some of the materials that are used for those applications. Let's see if I can advance my slide. I'm going to be talking about basically four topics. What is the threat we're trying to deal with, some radiation detection basics, the application to border security, and then some challenges and solutions. If we look at our ports of entry to countries such as this seaport, these were never built for preventing terrorist threats from entering countries. They were built for speed of commerce in general. So we're looking at how to prevent threats from entering such locations. The sorts of threats that we're concerned about are, of course, first off, weapons of mass destruction that could be put into containers, for example, or improvised devices that could be created by smaller groups. The material, special nuclear material, that is plutonium and uranium that could be used for such weapons. And in addition, we're also concerned about materials that might be used for radiation dispersal devices, that is radioactive materials that might be used for medical applications or industrial applications that are then used with conventional explosives to create havoc rather than mass destruction. For example, on the right-hand side, I show some pictures of some of these orphaned sources that are just stored out in fields or left at junkyards that are of concern. So let me give you an example of what a radiation dispersal device might do if it were deployed. And there have been a few minor incidents involving such devices, but this was actually not a RDD event, but rather it was an accident that occurred in 1987 in Guyana, Brazil. There was a large cesium source used in a medical facility. The medical facility closed, and the very, very radioactive source of cesium was taken by a junkyard dealer back to his junkyard, and unfortunately he opened it up, and children played with this powder because it glowed in the dark. And it took 11 days to discover this incident. And that occurred 100 miles away when somebody detected the contamination, the radioactive contamination. As a result of this accident, 4 people died: the junkyard owner, his wife, his child, and one of the workers at the junkyard. 28 others suffered burns, and a bunch, 250 or so, were contaminated. But the point of this is that 112,000 individuals sought medical care because they were concerned about this event. They hadn't necessarily been exposed, but they overwhelmed the medical community with their concerns. The pictures at the bottom on the right is a picture of a skin burn that's caused by this material. And on the left is the cleanup result of a lot of containers of material that, dirt that was picked up, and then cement covering contaminated materials that were picked up as a result of this contamination that cost about $20 million to clean up. So anyway, that's just one example of the concern of threats we have. And so now let me talk about radiation detection. Radiation detection is involved with detecting alphas, betas, gammas, or fission products. You're probably familiar with these terms. Alpha decay is the emission of a helium nucleus by another nucleus, a heavy nucleus like uranium. Gamma decay is the de-excitation of an excited nucleus, emitting high energy photons. Fission is the process by which a heavy nucleus falls apart into multiple pieces, including radioactive daughters and neutrons. And beta decay is the process by which a neutron or proton inside a nucleus emits an electron, an energetic electron. So these are the 4 basic emission processes for radioactivity. And we want to be able to detect these radioactive particles. Let me point out that all of us are subject to radiation. There's background radioactivity everywhere. There are sources from cosmic rays. There are sources from radon coming out of the soil, emitted from the uranium chain of decays. There's direct radiation from the soil, from uranium and thorium and potassium. There's radioactivity in the foods we eat. And then there are man-made things like medical exposures, which subject us to radiation. So in all, we are always subject to background radiations. And this occurs depending upon altitude and location, local geology, how much medical exposure you get, and if there's any work exposure, or flying in an airplane affects the background radiation we get. So we are always subject to radiation. And what we want to do is detect radioactive materials at levels that are maybe hidden by this background radiation. So I mentioned that there are these forms of decay that involve emission of high energy photons or electrons or neutrons. In general, all of these materials and muons that come from cosmic rays, as well as X-rays, interact with matter by producing energetic electrons in those materials. So when one of these radioactive particles enters a material, it ionizes the material it hits, it produces free electrons, it breaks up molecules, and produces chemical constituents, the ions, which may be active. All of these radiation forms, therefore, produce energetic electrons. That's sort of the end result. And if we have a biological effect, it occurs because of the chemical changes that occur, as well as the free radicals and electrons that interact and may attack cell components. So there is a biological effect that can occur. And of course, the human body is designed to protect us against certain levels of radiation because we are subject to background radiations at all times. But now let's talk about how we detect this radiation with instruments. You can build instruments that are gas-based or scintillator-based or solid-state-based. Those are basically the three categories of detectors. If you look at a gas counter, the best example of a gas counter, which you might be familiar with, is a Geiger counter. A Geiger counter is a gas-containing instrument. A radioactive particle enters the gas, it produces ionization, it produces free electrons. Those electrons are attracted to a high voltage wire in general. At that wire, they get amplified by cascading, and then that electrical signal is amplified, and that gives us a detection of an event. This detection does not produce any real energy information, it just says there is radioactivity present. The second class of detectors involves materials that are solid, and these are materials which scintillate. That is, they emit light when hit by an energetic source. So if a gamma ray or a beta ray or an X-ray or even a neutron impinges on a scintillator, it then emits light as a result of that ionization that occurs within the material. These can be both organic and inorganic materials. A best example of an inorganic material is sodium iodide, which is used in many handheld devices shown here on the bottom right. Another example of an organic is simply plastic. Clear plastics, which have small amounts of fluors embedded in them, can then emit light that is collected by a photomultiplier tube or a solid state photomultiplier tube. And that light is then amplified, and that gives a signal out of these detectors. The middle picture at the bottom shows what are called radiation portal monitors. These contain very large panels of plastic scintillator that are used for detection, for example, at border crossings, such as shown here in the picture. The third class of detector materials are solid state devices. These are germanium or silicon-based devices, semiconductors, very high purity devices. And you create a PN junction in these materials and you put an electric field across them. And therefore, any electrons produced inside materials by ionization can be collected, amplified by electronics, and give you a signal. Now, these solid state devices tend to be very expensive, and they also tend to be fairly small, but they do give the very best possible resolution. On the left here is an example of a high purity germanium boule with a detector contact at the bottom of it. You can see there, that's where the electronics connects to amplify the signal. The right-hand picture shows a energy spectrum of what you see out of one of these detectors. The very sharp lines seen here in this spectrum come out of this germanium detector. And they have a resolution of about 0.1% in energy. So they're quite good in terms of energy resolution. They're the gold standard. The dashed curve along the top is what plastic scintillator sees. In other words, it sees a very broad spectrum. It doesn't give you any details. But a plastic scintillator, very large plastic scintillator, is far cheaper than this small germanium detector. So there are trade-offs in terms of what you can actually do with these different materials. So with that brief introduction to detection, let me talk about the application to border security. Shown here is another example of radiation portal monitors at borders. Inside those white boxes there are large plastic scintillators and neutron detectors. If you look at the world commerce, every year, every day, thousands and thousands of containers are transported. For example, Los Angeles in the US gets over 7 million containers a year. These are 20-foot shipping containers. Hong Kong, over 20 million per year. The Netherlands, over 7 million per year. So these are very large volumes. And if you want to screen this material for potential radioactivity, whether it be radioactive materials that are there by accident, which does happen, contamination, or whether they are weapons of mass destruction or materials for weapons or RDD materials, you have to be able to handle these volumes of commerce. If we look at the United States, shown here are all of the border crossings to the US. Along the northern border with Canada, there are many land border crossings where vehicles, trucks, and cars cross, as well as people. On the southern border, there's the border with Mexico, again with land borders. On the west coast and east coast and along the Gulf Coast, there are seaports where all these containers come in, as well as other materials. And there are even seaports up along the major rivers into the center of the US. All of these are border crossings that have to be screened for materials. And the yellow dots represent airports where air cargo can come and go. So all of these require detection. And one of the programs that I've been involved with is in fact doing that. Every one of these locations does have radiation detection equipment at it for the possible interdiction of radioactive materials, whether it be by accident or by intent. As I mentioned, the workhorse detector that's used for this type of application are these radiation portal monitors. They're the big yellow things shown here, which cars and trucks drive through. So if you drive through the Canadian border or the Mexican border, you will see such devices. Here are some more examples of them. On the top left is an airport where cargo is screened. On the top right is screening occurring at a mail facility or a package facility. On the bottom right is another land border crossing for vehicles, cars. We can get huge quantities, 50,000 people per day may cross at some of these border crossings. And the bottom left is an example of a mobile detector that is used for special applications. In addition to those types of passive radiation detectors, there's complementary information obtained from such things as imaging. These are X-rays basically. There are X-ray devices at border crossings which screen trucks looking for hidden material, smuggled material. In this case, on the upper left is an example of people crossing the southern border that are observed inside of a container. In order to enhance the ability of passive detection and radiography, there has been recent development in what's called active interrogation. In this case, there again is passive detection, but there is also a radioactive beam of typically high energy X-rays that are shown onto the vehicle. And then you look for the results of that incoming radiation producing outgoing radiation. That's called active interrogation. This type of technique has been deployed in test facilities, but it turns out to be very expensive, very large in footprint, and has obvious limitations due to radiation exposure. So it's not clear whether this technology will ever be deployed at typical borders. So now let me turn to some challenges that occur for this application, just a couple examples. The first problem is what are called nuisance alarms. That is, you're looking for threat materials or contaminated materials. The biggest background problem you have is from naturally occurring radioactive materials. I mentioned that we are exposed to radiation all the time. Basically, every piece of dirt or every piece of building material is radioactive. And so if you have those in large quantities, they can produce alarms, which are a nuisance. They aren't of concern, but they do take time and effort. Other examples are agricultural products like fertilizer, kitty litter, which is used widely, is basically just dirt. Ceramic materials, propane tanks, because when you take propane out of the ground, radon comes along with it, and you can see the radon daughters. Road salt's another good example on the northern border particularly. And medical radioisotopes. I should mention that in the US, 1 in 2,400 Americans carries a medical burden of radiation large enough to produce an alarm at a border crossing. I also want to mention that food products like bananas do not produce radiation alarms. The packing density of these materials is not high enough, even though they contain potassium-40, which is radioactive. They do not produce alarms because there's not enough of the material there in a vehicle or a container to produce an alarm. And that is sometimes erroneously reported in the press that they do. In addition, there are some neutron alarms which come from the presence of nuclear fuel, for example, or well logging sources, which are used for searching for oil and gas, or for commercial applications. Another example of a problem we have is the degradation of these detection materials. I mentioned plastic scintillators. It turns out plastic scintillators do age over time. They can get surface crazing, which is a surface defect. They can get surface clouding, and they can get internal fogging. The internal fogging is produced by the presence of humidity. So hot, humid conditions, these instruments are used outdoors. Hot, humid conditions can push water into the material. And when it gets cold outside, this water condenses and produces this internal fogging, which generates defects at the micron level inside the material and produces aging. So a lot of time has been spent looking at these sorts of problems in materials and trying to solve those problems or reduce their impacts. So let me just conclude by saying, this is an important field. I've only touched on one application that is for international borders. Norm alarms and medical alarms turn out to be the operationally limiting problem we run across. I didn't talk at all about computer simulations, but that's exceedingly important to this type of work. And finally, in general, gamma ray detection and neutron detection are very active fields of research today and will continue to be so. So with that, I thank you. I acknowledge my sponsors, and I'm available for any questions you might have.
So thank you.